Okay, this is study stream 6. Okay, so I now need to, every now and then I need to touch the mouse because I'm busy studying. And if I don't, the stream cuts out. All right, so this stream, I'm going to run downstairs at some point during the stream to get some coffee. Anyway, I was using the back of papers around me to do calcs, and I was using my assignment papers where I had my rough calculations for my assignment. When my calcs were finished, I threw them away. So I threw my assignment rough calculations away. Luckily, I've retrieved them. Okay, so now, this is not assignment as well, is it? And it might be, but this I can redo again. It's fine. This is simple. And this, yeah, this is trivial. Okay, so this I can definitely throw away. And this, what is this? Yeah, this is also relatively trivial. Okay, I can use the back of this paper. And this to be recycled. Okay, good. And I can use this half. I don't want to waste this paper. I can use all of this paper. Okay, good. So now let's get to the next activity. Next exercise 5, page 19. We have to check equation 21 does satisfy the diffusion equation and the boundary conditions of example 4, both x equals 0 and x equals L. Okay, so let's first write down the equation, which is theta of x and t equals sigma from n equals 0 to infinity of a sub n cos k sub n x e to the minus d k sub n squared t, where k sub n equals n pi over L. Okay, so that's our solution. So we're going to think about the diffusion equation. Diffusion equation is going to be theta, it's going to be d theta dt equals d second partial derivative of theta with respect to x. Okay. All right. So first thing to do is take the partial time derivative and see if it equals the other side. Okay, let's take the partial time derivative. So if we do that, we're going to get the only thing that's in t is this equation. The rest is all in x. So I think we're going to get sigma from n equals 0 to infinity an cos k and x. And then we're going to take this derivative, so we're going to pull down minus d k sub n squared. And then we get e to the minus d k sub n squared t. So that's going to be our left-hand side. And now we do the right-hand side and see if it equals the left-hand side. So the right-hand side, we're going to come back to the cos. We're going to pull out a minus, and we have a d. So we have a minus d, or we have a d, so now it's a minus d, and we're going to pull out two k's. We're going to get kn squared, which is exactly what we have there, and then everything else is the same. So just by inspection, you can quickly see that it does, if you substitute it into the diffusion equation, it's satisfied. But then for the boundary, then the second part of the question says, at both x equals naught. So at x equals naught, we're going to get, this is going to go to 1. And okay, let's see, at x equals naught, this goes to 1. So x equals naught, this is going to go to 1. Then we get this minus dk and squared factor. We got all that. All right. It doesn't matter what we put in, because both sides are the same. We've already shown that both sides are the same. And if I put x, so if both sides are the same, both sides are the same. Okay, let's see what the answer says. Where do I find the answer to this? Just duplicate that and scroll down all the way. Really hungry. Oh, it's a solutions. Here we go. Okay, solution to exercise 5. So we got that, we got this, yes. And then they're the same. That's what I said. Okay. Oh, yeah. Oh, right. Those are the boundary conditions. So this is not correct. At x equals L. Oh, right, because we have to stick in the K. So it does work. Okay, good. I see. All right. And exercise 6 is going to be a rather big one. Exercise 7 is also a big one. What do I have on the agenda today? We have exercise 6 to do now, and then we're going to go. And then that's it. So this is the last exercise, exercise 6. We want to get up to, we're not going to do exercise 7 today, but we'll get up to exercise 7. So we're doing pretty well. That's our goal for today. So we have this big exercise coming now. All right. I am hungry. But I'll have a cup of coffee. And then after the coffee should help me get through exercise 6, and then I'll just quickly read the last bit, and then I'll end the stream and have lunch. Okay, reserve my lunch, and then I'll come back here and work on my assignment. Probably the end of studying for today. Okay, so and later I have to work on my dissertation. I've got to look at the papers, my key papers, and try and work out how to hone my objectives, and I have an idea, but I need to confirm that, email my tutor supervisor. I need to do that later. I also need to email this module's tutor, just touch base. I also, as I said, I was going to do the TMA assignment, tutor marked assignment, and work on that after this. What else do I have to do today? I'm hungry. Okay, I'll have to watch the podcasts that my tutor created for us. Need to work on my dissertation log. I've got to finish one tutorial video. Do a chest workout. Yeah, so that's my agenda for today. Still much to do. Okay, so let's continue now. The coefficients AN in equation 21 remain to be determined. Okay, this is done by choosing them such that the initial condition, and this is the initial condition with boundary condition to be satisfied. So n equals 0, we'll give this. Okay, this can be recognized as a trigonometric Fourier series of the form introduced in Unit 2. All of the coefficients of the sine terms are 0. Oh, yes. And we did this in MST224. Yeah, we did this. And we had other ways of doing it. But yeah, it's coming back to me. So the next exercise applies the results of example 4 to a situation where a poker. Okay. Let's see. Poker is then taken out of the fire. Okay, let's do it. Exercise 6. All right. Consider the temperature distribution in a long, thin metal rod of length L. Okay. The temperature can be modeled by one-dimensional diffusion equation. Okay. So initially, the rod has the end where x equals 0 maintained at temperature theta sub naught. Okay. All right. So it's maintained. So it's constant. Theta sub naught, so it's constant. So I could say that partial theta d theta dx at x equals 0 equals theta naught. And that's only at the 0 end, right? And then at the other end, where x equals L, it's maintained at temperature theta L. So we can say d theta of L dx equals theta L. So we have constant temperatures at both sides of the rod, different constant temperatures, theta 0 and theta L. So the rate of change is constant. There's no rate of change is constant. So we have those two equations. The rate of change of theta at x equals 0 and x equals L is theta 0 and theta L respectively. Okay. All right. So what's next? I got this. Okay, so solve the diffusion equation in the steady state. So these basically are boundary conditions. So we're going to use these boundary conditions later on. But the first thing to do is just to solve the diffusion equation and show that the general form for theta x in this case is theta x equals ax plus b. Okay, now I know we're going to get to the general solutions of a simple harmonic motion. So I see this form ax plus b. So that's the case where mu equals 0. So we have to show that the mu equals 0 is the only case. So in other words, mu, positive or negative mu, don't apply to this problem. Because we've got to show that the general form of theta x in this case is theta x equals ax plus b. Okay. Okay, so why? Why do we not have a positive or negative mu? Okay, well, let's explore this. I think I'm going to go get some coffee now. At least I have an idea of the problem. Okay, I'm going to go get some coffee. Basically, I'm going to go through all of the steps that I just went through a second ago with the other problem. Okay, let me just, before I get the coffee, because it's not quite 11:30, 11:29, let me just make a start. So I'm going to say, let me write down the heat equation. So d theta dt equals d second derivative of theta with respect to x. That's the heat equation. I'm very familiar with this equation now. Okay, now we're going to use separation of variables. So we're going to say that equals, so we're going to say let theta of x and t equal x of x and t of t. Okay, we substitute that into the equation. And so we are going to get then, it's only t, we're going to get x of x, t dot of t equals d x double prime of x t of t. Okay, and then we're going to divide by xt. So we divide by x on this side. This x is going to cancel, and we're going to get t dot of t over t of t equals d x double prime of x over x of x. And they're both equal to mu. That gives us our two equations, the same two equations from the last example. Okay, and then we get d dot of t equals t of t times mu, and then we get, and I could put the d with the mu, and I think I did that because this let's have a look at the general. This is important reference, so we don't have to start everything from scratch every time. Because we could go through the integrating factor method and solve them, or we can just look at the solutions that are known. So These are known solutions, so we're going to go through these. So we have T dot of T equals T of T times mu, which looks like the growth decay equation. So we know the general solution of the growth decay equation. So I'll put the D there again, like the last time. So we know that this has the solution. What's the solution of this? It's going to be T of T equals A e to the mu dt, mu dt. Okay. So this is our time equation. So when we put everything together at the end, we're going to, because we know that theta of x and t equals x of x times t of t. So this is the times t of t part. This is like the phase factor in quantum mechanics. Okay, so it's just really like the phase factor of quantum mechanics. Okay, good. We got that. That's easy. Now we look at the other, the x. Where's our x equation? So we have x double prime of x is going to equal mu of x of x. Okay, and that looks like a simple harmonic motion. Okay, now we have three cases. We have the case where mu is positive. We have the case where mu is negative, and then when mu equals 0. Now, our boundary conditions say that the derivative of theta with respect to x equals theta naught at x equals naught and theta L at x equals L. And I know because it says here that we're looking for the solution of mu equals naught. So I have to show that mu equals naught, basically. That mu must equal naught. That's basically what we're doing. We're trying to prove that mu equals naught. Okay. So how are we going to show that? So let's just go through case by. Let's just first do this mu equals naught case. So if mu does in fact equal naught, then x prime of x, let's say x prime of naught, which we know equals theta sub naught, would then equal, if we take the x prime, that's going to be a plus b. Yeah, a plus b. So that means that a I used a for my coefficient for the time part. I'm going to change that to alpha. Okay, that's going to be alpha. So theta naught equals a plus b. So, so a equals theta over b, or b equals theta over a. No, I mean minus a. I'm saying over. How does it really help me? So I'm going to just write that down. So a equals theta naught minus b, which is equal, three-line equal, which is exactly equal to b equals theta naught minus a. Okay, explored that. We don't have any. Okay, I'll just keep that. Let's have a look at the second condition. Now there's no, this derivative is independent of x. This is independent of x, so I can't apply the L boundary condition because there's no x. Yeah. Okay, let's keep that there. And then what about the other situations here? Okay, let's do that top one, which is when mu is positive. There's nothing that says that mu must equal 0. Because physically, what is mu? Mu is just mu is basically like phi in quantum mechanics. It's just the partial derivatives are both equal to this thing. It's the energy. No, that's the energy in quantum mechanics. It's the energy. In quantum mechanics, mu is the energy. Okay, I'm going to come back. I'm going to have coffee. It's 38. Okay, so I think I deserve a coffee. I need a pee as well. So that's the sign of drinking lots of water. So coffee break. Back in 5. All right. Back in 5. Ah. Okay. All right. Back. Beanies, double chocolate coffee. Fantastic stuff. All right. So where were we? All right, let's continue. Okay, so we want to explore case when mu equals greater than 0. So if we explore that case, what do we have? We have x prime of x equals AR e to the RX minus BR e to the minus RX. And then at x equals 0, we have theta sub 0 equals sub 0, cold theta. Okay, so then we have, what do we have? We have, so these exponentials go to 1. So we're going to have A minus B equals A minus B. Equals. So since we have these constants, it's these boundary conditions, it's trickier for me. It's not 0. So we have R A minus B equals theta sub naught. And then the other one is we have theta sub L equals okay. Delicious. Okay. So we have a or e to the RL minus b r e to the minus RL. We can times both of these by e to the RL, times everything by e to the RL, and we get equals AR e to the 2RL. Oh, we can't do that. Because then the other side will be the same. No. It's not equal to 0, so I can't use that trick. Okay. I'm not sure why. Okay, I'm going to take a peek at the solution. Giving it a good go, looking at the time here. Okay, where's the solution? Solution to exercise 7. Okay, let's see. Okay, let's see if at least my thinking was right here. All right, so I'm looking at the right. Oh, exercise 6. I'm looking at the right. Solution to exercise 6. Okay. All right, let's see. In the steady. Of course. That's where I went wrong. No, I didn't go wrong. My boundary conditions still apply, but I didn't apply the initial conditions. So I applied the boundary conditions, but I didn't think about the initial conditions. Okay, I'm just going to read through the solution, and then I'll think. Let's just read through the solution. Whew, I am so hungry. I'm so hungry. This stream has been going for 40 minutes. I'm going to read through the solution, and I'm going to read through the rest, and then I'm going to go to lunch. Okay, so let's see. In the steady state, the temperature is independent of time, so we have the time derivative equals 0 because it's steady state. Yes. Yes. Okay, the temperature only depends on x. Okay, so the diffusion equation. So let's just take that. These I still need. Keep these over here. So let's just rewrite the diffusion equation because the left-hand side of the diffusion equation becomes 0. So 0 equals d, and then d prime prime of x. Okay, so that's the diffusion equation. That's very simple. Or we can divide by d. So that also means that the second derivative of x equals 0. We also know that makes sense because the first derivative of x, this is x, with respect to x is going to be a constant on either side. And because that's the case, the derivative of that constant will be 0. So of course, and I could have even thought about that. Even if they don't tell us about that, you can come to this understanding in another way because we know that the spatial derivative on either side of the rod is constant. So that means that the second derivative is going to be 0. The second derivative, spatial derivative of the heat equation will be 0 at either end. Because we know the first derivative is a constant at either end. And secondly, we know that the steady state, so the time derivative is equal to 0. So the left-hand side of the heat equation, d theta dt is equal to 0. So we have 0 equals d theta, second derivative of d theta with respect to x. Okay, so we have that. Okay. And that's it. And that's it. And all you do is, how do you solve that? If you have an equation, you divide through by the diffusivity constant, and then you just have the second spatial derivative then you have the second spatial derivative equals naught. We just integrate it twice. You get two constants of integration. You get x equals integrated once. Because it's 0, you get a constant. You integrate it again, you get ax plus another constant. So you get ax plus b. And that's it. Okay, so that's part A. Solve the equation. Okay, so A is done. Now we're going to do B and C. Okay, so B. Let's have a look at B. So that's A. Let's have a look at B. Okay. So B, we know A. Let's move to B. Look at the answer. Okay. Now, suppose that the ends of the rods are no longer maintained at fixed temperatures. Okay, at the same instant, the rod is thermally isolated. That is, no heat flows into or out of the rod. Let's just read that again. Now, suppose that the ends of the rod are no longer maintained at fixed temperatures. So the temperatures at the ends of the rods change. So d theta dt is changing. Equals t. So it's going to change with time. Alpha t. Okay. But at the same instant, the rod is thermally isolated. That is, no heat flows anywhere. So we have no heat flow, but we have changing temperatures. The initial condition is that the rod has the temperature profile calculated in A. And so show that the time dependence of the temperature from the moment the rod becomes thermally isolated is given by and we have this equation theta of x and t equals theta naught plus theta L over 2 plus 2 theta L minus theta naught over pi squared times sigma from n equals 1 to infinity of minus 1 to the n minus 1 over n squared cos k sub n x times e to the minus d k squared k sub n squared t, where k sub n equals n pi over L. Okay. Hint, the situation here is the same as in example 4. So equation 21, where's equation 21? Where's equation 21? Yeah, that's that. Equation 21 is our results from example 4. So equation 21, where are we? So equation 21 applies. The Fourier series for the even periodic extension of the function is given by this. So just, okay, so we have that Fourier series. Okay, so it's really just applying what we are told. We start with, let's just write it out. After this is done, I'm gonna make lunch. I'm very, very hungry. Okay, so this session was only, no, let's just finish this and then, yeah, and then we deserve some lunch. I'll eat lunch while I read. Read a little bit. Just a bit of reading. I'm not going to really make notes because I'm pretty good with this kind of stuff. So just a bit of reading, and then we're done with the studies for today. We can work on the assignments. Okay, so now let's just write down the solution. That's the, I think this equation is going to be important. Because this is quite a generic example. Because we have the generic example where we're applying the heat equation for zero Oh, no, this is those boundary conditions. Now we're doing initial conditions. Let me just write down the solution, but nonetheless, that's a pedagogical example that might be, it's worth knowing the solution to. Okay, so this is going to be theta. This is the solution from of x and t equals sigma from n equals 0 to infinity a sub n cos of k sub n x e to the minus d k sub n squared t, where k sub n equals n pi over L. That's our solution. Now let's just read what they're saying again. They're saying, now suppose that the ends are no longer maintained at a fixed temperature. So the boundary conditions are no longer constant. But at the same instant, the rod is thermally isolated, so there's no heat flow. So we're going to say T. So basically, So let's just set t equal to 0. I think that's where we set t equal to 0, right? Is that right? Yeah, why do we set t equal to 0? Which reads, you now suppose that the ends of the rod are no longer maintained at fixed temperatures. So the ends of the rod have changing temperatures. Temperatures change with time. The initial condition. This is not boundary condition. Okay, so we're starting from t equals 0. So we just do t equals 0. So we have theta of x0 equals, and this is going to go to 1. So we can have sigma n equals 0 to infinity of an cosine of k and x. This term just goes to 1. Okay. So we've got that equation there. And we have that other equation, the other equation that we worked out. We have that equation too. So theta, so we use that equation. Basically, that's what it's trying to tell us. It's telling us to use the other equation. So that's what it says. This is very important. The initial condition is the temperature profile calculated in A. So that's the initial condition. So that means that theta of x naught equals, and we have A, and we've calculated A and B. So let me just quickly write that down. So A equals theta L minus theta naught over L. And B equals theta naught. And our equation that we calculated in A is AX plus B. So AX plus B, which we can write as theta sub L minus theta naught over L minus theta naught. Okay. So we have these two equations. And then the second one, we have a trigonometric Fourier series, and they gave us the trigonometric Fourier series here. L over 2. Why is it of period 2L? It's period 2L. Okay, I'm very, very, very hungry. But I need to just endure. I need to get through this. Okay, so they gave us this hint. We need to find f of x. And we have cosine of k and x. So the sigma from n equals naught an, we've got to show that that equals all of this. Hint, the situation here is the same as before, so equation 21 applies. Okay, we've used that hint. The Fourier series for even periodic extension of a function is for x equals 0 to L, but it's even, so it's 2L. Okay, because it's even, so it's a 2L situation here. Okay, so we have 2L. So I'm looking at the solution. It's hard for me here. So this is a trigonometric Fourier series with all of the sine term coefficients equal to 0. Yeah, this is because we have it as a cosine. Okay, that's fair enough. So we need to calculate the Fourier series of the even periodic extension of the initial temperature distribution. Fine. Period 2L, fine. This is where we can use the second part of the hint, which gives the Fourier series for an even periodic extension. Fine. The initial temperature distribution of theta x naught can be obtained from the f of x given in the hint. By multiplying by a and dividing and adding b. Oh, I see. Because this equals this. That equals, so we equate these two sides. We multiply both sides. Then we divide both sides by a to get rid of the a. So this is multiplied by A, this is add B. So this here in parentheses is just this expressed as the Fourier series given. And then this is just multiplying by A and adding B. Because we have a difference. Because this AN, we're trying to find what this AN is, and the AN is just basically that. Is that right? Because we have all of this equals all of this. Okay, I'm going to stop the stream right now. That's it. This one is quite a hard one to unpack. I need to pee again and I'm hungry. That's it for streaming today. I'm not finished with this question, but I need to pee. End stream.